Friends, today we are going to discuss about the topic transformer and AC power transmission. Unit 4 electromagnetic induction and alternating current, which is belongs to class 12 Tamil Nadu State Board physics. Actually, what is called a transformer? Transformer is a stationary electrical device that transfer the electric energy from one circuit to another through an electromagnetic induction. It is one of the most essential component in the modern power distribution system. Okay, as the transformer having no any moving parts, it is called as stationary device. The energy transfer is purely electromagnetic operations, and here the frequency will be constant. The output frequency will be equal to input frequency. There is no any change in the frequency. And the power system, it is essential for long distance AC transmission. Principle of the transformer. Actually, the basic principle of the transformer is mutual induction. That is mutual electromagnetic induction. What is meant by mutual induction? When the alternating current flows through the primary coil, it produces continuously varying magnetic flux. That is time varying magnetic flux. This flux will be linked to the secondary coil. See, through the soft iron core. According to electromagnetic induction, the change in magnetic flux induces electromotive force in the secondary coil. The magnitude of induced EMF depends on time varying magnetic flux and number of turns in the secondary coil, which is given by the equation E is equal to N into d phi N into d phi by dt. Okay, so the amount of induced EMF, that is the magnitude of induced EMF, depends on number of turns and rate of magnetic flux. Here, note the key points. There is no electrical connection between the primary and the secondary coil. There is no physical contact at all. The energy transfer is purely magnetic. Okay, the next one is construction of the transformer. See, the transformer consisting primary coil, secondary coil, laminated core, insulation and a cooling system. Primary coil, the number of turn is referred as NP. That is, the primary coil is connected to the supply source. Okay, see, the number of turns in the primary coil determines input voltage handling, and secondary coil, the number of turns is represented as NS. Here, the secondary coil delivers the transformed voltage to the load line, and the number of turns in the secondary coil determines the output voltage. And next one is a laminated core. See, soft iron with the insulated thin sheet. Soft iron with the insulated thin sheet will be used as a laminated core. Why we are using the laminated core? It considerably reduces the eddy current losses. That's why we are using this laminated core. Next, insulation and cooling system. Why we are using the insulation? See, it prevents the short circuit between the primary and the secondary turns. Actually, in the both the primary and the secondary coil, the wire will be wound one over another. So that is possible for the short circuit. So avoid the short circuit, we are using the insulated copper coil. Cooling system. The oil will be maintained inside the transformer box. It maintains the optimal temperature. Okay, next one, working. working of the transformer. Actually, the energy transfer process. This is when the alternating voltage is supplied to the primary coil, an alternating current will be flows through it, which produces alternating magnetic flux in the soft iron core. That is, time varying magnetic flux will be linked to the soft iron core. So here this alternating magnetic flux linked with both primary and secondary coil. So in the primary coil, this time varying magnetic flux will be produces back EMF. This back EMF will be opposes the applied voltage. This time varying magnetic flux will be produce the forward EMF in the secondary coil. So this forward EMF drives the current through the load. See, we can simply understand by the block diagram. See, AC voltage is applied across the primary coil. See here. Here AC voltage will be applied and alternating magnetic flux. This line and all magnetic flux. This will be linked to the core and this time varying magnetic flux will be induces the EMF in the secondary coil. In this secondary coil, induced EMF will be produced. This is the working of the transformer. Next one is transformer equations. See, here given transformer ratio. The two ratios given here. One is voltage transformer ratio, which is Vs by Vp is equal to Ns by Np. So actually this equation is from Vs by Ns is equal to Vp by Np. Actually, what is the meaning of this equation? The EMF per turn for both primary and secondary will be equal. In this equation, Vs is the secondary voltage, Vp is the primary voltage, and Ns is the number of turns in the secondary coil, and Np is the number of turns in the primary coil. Next one is current transformer ratio. Usually the current transformer ratio formula is given here. Is by Ip is equal to Np by Ns, or Ns by Np, Ns by Np will be equal to Ip by Is. So this area only many students will make mistake. Vs by Vp is equal to Ns by Np is equal to Ip by Is. Instead of Ip by Is, most of them will be right. Is by Ip. So this will be make mistake. So both the two equations we can written as by combined equation. Vs by Vp is equal to Ns by Np is equal to Ip by Is, which is equal to K. K here, the transformer ratio. See the important note. The voltage transfer ratio is inverse to the current transformer ratio. That means what? If voltage increased, current will be decreased. So by stepping up, the current will be reduced. Here, ideal transformer condition is given. What is that? Ideal means there should be output will be equal to input. See, given here, that VPIP is the input power that must be equal to Vs by IP, that is output power. That means that 100% efficiency. Next one is types of transformer. Step up transformer and a step down transformer. Actually, what do the step up transformer and what do the step down transformer? Actually, the step up transformer condition is Ns is greater than Np. That is, number of turns in the secondary coil will greater than the number of turns in the primary coil. What will do? The step up transformer increases the secondary voltage and decreases the secondary current. And it will be used at the power generation station, and it will be enabled to long distance AC transmission system. And step down transformer. The condition for the step down transformer is number of turns in the secondary coil will be less than the number of turns in the primary coil. Actually, what will do the step down transformer? It reduces the output voltage and increases the current, and it will be used in the power distribution substations. We know that in our city, outside the city, there will be the substation will be provided, so that will be distribute the power to the domestic electric purpose. So it will provide safe domestic voltage. Typically it is 230 voltage. Okay, the next one, efficiency of the transformer. Any device efficiency means it can be calculated by the ratio of the output to the input. Here, that the efficiency of the transformer is denoted by the symbol eta. The efficiency of the transformer can be defined as the ratio of the output power to the input power. So here the equation is given, eta will be equal to output power divided by input power into 100%. This equation alternatively can be written another form, that is eta is equal to output power, this output power divided by output power plus power losses into 100%. This also will give the efficiency of the transformer. Typically, a transformer produces 96 to 90% of efficiency. A well-designed transformer achieves remarkably maximum efficiency, but not 100%. Why not 100%? There will be the small amount of energy will be lost due to resistance of the coil and properties of the magnetic property of the core and the flux leakage. However, the transformer will produce most efficiency. That is most efficient component. The next one is energy losses. Actually, the transformer experiences energy losses due to heat production. Okay, while the current flowing through the coils, it will generate heat, that is unwanted heat. We are transferring only energy. We are not producing heat. So here, due to some of the reasons, energy will be losses. What are the types of energy losses? First one is hysteresis losses and eddy current losses and copper loss and flux leakage. Here, first one is hysteresis loss. Energy will be wasted repeatedly magnetizing and demagnetizing the core by the AC cycle. So, this can be reduced by using soft iron with a low hysteresis property and eddy current loss. See, the transformer core is the thin sheet in which the circulating current will be produced. So, the circulating current is nothing but eddy current. So, this will be generated unwanted heat. Okay, so this loss also has to be reduced. How can we reduce? By using laminated sheet, by using laminated core with the insulated thin sheet, we can considerably reduce the eddy current loss. This hysteresis loss and the eddy current loss both are termed as core loss and also called as iron loss or constant loss. Here, next one is copper loss. We know that according to Joule's law of heating, if current flowing through the conductor, the heat will be generated. This is unwanted heat only. So this can be, this resistance of the primary and the secondary coil windings causes heat dissipation. Okay, so it can be reduced by using thick copper wires. Okay, why we are using thick copper wires? Actually, the resistance R is directly proportional to L by A. That is, resistance directly proportional to length of the coil and inversely proportional to the area of the coil. If we increase the area, if using thick wire, area will be increased. Area increased means the resistance will be decreased. Consequently, the heat loss can be reduced considerably. That is I squared R. Next one is flux leakage. Actually, not all the magnetic flux will not be linked to the both primary and the secondary coil. A few of the magnetic flux will be linked to the surrounding. So what we have to do? We have to use well-designed core and tight winding arrangement. And also by using tight winding arrangement, we can considerably reduce the flux leakage. See, the exam point of tips given here. Already I told this hysteresis loss and the eddy current loss also called as core loss and also called as iron loss or constant loss. Okay, the copper loss is a variable loss. So it is depends on the load current. The next one is advantages of AC in a transmission. See, this is an important note. See, why we have prefer the AC to the long distance power transmission than DC. Here, the AC can be generated at a low voltage. Okay, typically it can be produced by at a voltage 11 to 25 kilovolt. And by using that step-up transformer, the voltage can be increased to 220 to 40 kilovolt. Okay, and we can reduce the current, that is reduces the copper loss. By increasing voltage, we can decreasing the current. As I said already, voltage transformer ratio and the current transformer ratio will be inverse. So, if you are increasing the voltage, current will be decreased, thereby power will be constant. The same power. So, it drastically reduces the heat loss in the transmission line. Then, step down at the substation. While we are receiving the power from the generation station to the substation, in the substation, by using the step down transformer, we can reduce the voltage to the safe level, that is typically 230 voltage for domestic purpose and 440 voltage for the industrial purpose near the consumers. And see, that's all. And board exam point of view given. Simply the transformer power loss can be reduced by stepping up the voltage. Current will be reduced. Stepping up voltage, current will be reduced. This will be makes I squared R losses extremely small. That is energy loss due to heat loss due to Joule's law of heating. And this will be makes AC power transmission more efficient than the DC power transmission. Okay, students. Hope you understand clearly. If you any doubt, you can ask by the comment. Thank you for watching. Thank you.